In this video, I want to cover some basic concepts of probability and what's called statistical inference. It's really subject matter for a later course. This is just to introduce you to the idea. And, uh, and we're not going to use it very much in this course at all, except that it's lurking in the background whenever you look at data to understand sort of the statistical foundations of what it means to look at data. So as an example, I want to start, I have a little data set here from a survey that's done in the United States of people and how they use their time. And so in this data set, this is actually a random sample of 9,435 people in the US and how many minutes a day they spent on various activities. What they do is they keep a diary of how they spent the day, and the survey is done of the previous day, asking people, how did you spend your time? And I'm just going to focus on one of these variables right here as an example. This is minutes spent watching TV or movies. And if we get a picture of this, when we do it in Graph Builder, take TV movie time and look at a histogram of that. And in fact, let me add on some percents here. So these are in sort of big blocks. These bars are pretty wide. We could make them narrow, but let's just use this big block. Well, when you look at this distribution, first of all, the shape, it's a very skewed distribution. Most people look like they're in the bar between 0 and 200 minutes. So that's 3 1/3 hours a day, which is quite a bit of time to spend in front of the screen, but that is at least what Americans do. And you can see that there's a relatively small number of people. I mean, 8% watch between 400 and 600 minutes a day. We could talk about what is the probability that a randomly selected person in the US watches more than 600 minutes a day. 600 minutes is 10 hours. So look at the percents, 4%, 1%, and these are too small to measure. So it's on the order of about 5%. About 5% of Americans watch more than 10 hours a day of TV and movies. You could interpret that as a probability. In fact, the most basic concept of probability is to talk about a relative frequency. How frequently do you encounter people that watch more than 10 hours a day? And at least based on this random survey, it's about 5% of the time. We might also be interested in something like the mean of that column. And let's just look at the average. $189 minutes, almost exactly 3 hours. So based on this survey, we would say the average American watches about 3 hours of television a day. There is a problem, though, in that the true statement would be out of the 9,435 people that were surveyed, the average time spent was 189 minutes. So what you really want to know is, what is the average time spent by all Americans, not these 9,435? That is a basic question of statistical inference. Or posed in terms of probability, you could say, well, how likely is it that the average American watches about 3 hours a day? And since there's over 300 million Americans, the idea that 9,435 tells you something about the 300 million seems like a bit of a stretch to jump to the conclusion that this 189 is representative for all the population. So that requires us to do something called statistical inference and ask the question, what can we infer about the overall population. We're not interested in these 9,435 people that were randomly selected. We're interested in the country as a whole, what it represents. So that's the basic question of statistical inference. So to answer that question, let me switch to a different data set first. This one I provided for you, it's called the central limit theorem, and this is sort of the basis of what underlies all of statistical reasoning. So you'll notice I have 6 columns here and no data. Each of the columns has a formula behind it. Let's look at what this first column has. It's kind of a messy formula. First of all, in this, it has this function called a random normal. The normal distribution is the most basic distribution that you can think of. It's a famous bell-shaped curve. And there are lots of things in nature that follow normal distributions. If you look at people's heights, it's approximately a normal distribution. If you look at people's intelligence scores, like an IQ test, it's approximately a normal distribution. In fact, most standardized tests that people take, entrance exams for college, they follow normal distributions. They're created in order to have a normal distribution for what results. Many things in nature are not normally distributed. The distribution we just looked at, television watching, was not a bell-shaped curve. It was a very skewed distribution. But right now I have here a normal distribution, and if you just use the random normal function in JUMP, it'll give you on average a value of 0, but a standard deviation equal to 1. That's called the standard normal distribution. It's a bell-shaped curve with a mean of 0 and a standard deviation of 1. And so what I'm doing in this column is I'm going to add up, that's what this summation sign means, I'm going to add up one value taken from the normal distribution and divide it by 1. So you think of it as taking a sample of size 1 and looking at its value. So adding up one value and dividing by 1 means just look at the value. That'll become clearer here in a second. If you look at the second column, I've told JUMP to go and choose 2 random numbers from that bell-shaped curve, add them together and divide by 2. So I'm looking at the average of 2 random numbers from the bell-shaped curve with a mean of 0 and a standard deviation of 1. And the other columns behave the same way. Here I'm going to take 9 random numbers, random draws from that bell-shaped curve, add them together and divide by 9. I'm looking at the average of 9 of these numbers. And so on. The average of 25 of the numbers. The final one is take 100 of these numbers, add them together and divide by 100. So to see what this looks like, let's add some rows. Let's go ahead and add 10,000 rows. And you can see the picture on the top, but let's look at it more closely. Let's look at the distribution for samples of 1. All I've done is draw 10,000 numbers from a distribution that is bell-shaped, has a mean of 0, and notice the mean here is pretty much equal to 0, just slightly different. The standard deviation is pretty close to 1. This is your standard normal distribution, just being reproduced by the computer. Using 10,000 random draws from the standard normal distribution, it's approximately replacing or reproducing the standard normal distribution. All normal distributions have a very attractive property. It's always true that about 2/3 of the data lies within 1 standard deviation of the mean. About 95% of the data will be within 2 standard deviations of the mean. And something like 99.6% of the data is within 3 standard deviations of the mean. You can see this sort of in effect here. 95% of the data should be within between the 2.5 percentile and 97.5 percentile. Notice the 2.5% point is reached at minus 1.96. 1.96 standard deviations below the mean. And the 97.5 percentile is at 1.986 standard deviations above the mean. Technically, it's 1.96 standard deviations below and above the mean will give you 95% of the standard normal distribution. But as a rule of thumb, just use the number 2. 95% of the time you'll be within 2 standard deviations of the mean. Over 99% of the time within 3 standard deviations of the mean. And notice 99%, all of the data is between 3 and 0.55 standard deviations below the mean and 3.95 above the mean. So this is very close to what you would expect from any normal distribution. 95% of the time you're within about 2 standard deviations of the mean, and almost 100% of the time within 3 standard deviations of the mean. You'll notice that these outliers, we have 10,000 data points, so there are a few outliers that are more than 3 standard deviations from the mean. This is what allows, when they do intelligence testing like IQ tests, and they say, well, you're in the 70th percentile on this test, that means that there are about 30% of the people that scored better than you and 70% that scored less. And if it follows a normal distribution, you could interpret, as soon as you know what percentile you're in, you have a rough idea about how likely it is that somebody scores higher or lower than you. And they generally follow normal distributions. So that's our sample size of 1, which is just saying, look at the 10,000 numbers that we've drawn from that distribution. Look at the shape for the average of 2, the average of 9, the average of 25. They all look like they're bell-shaped. But the numbers are actually different. So in fact, if we look at the distributions for all of these at the same time, they're all bell-shaped curves. But when you look at the actual numbers here, notice the scale keeps changing. This one goes up to 4. This one goes up to around 2.5, 1.2, 0.7. So let's put them on the same scale. Well, now something different happens. Here we have a range from about -3 to +3. Here we have a range from about -2 to +2. Here we have a range from about -1 to +1. If you want to add some more bars in there, click on the hand tool and let's add some more bars. So what's happening to these distributions? They remain bell-shaped, but they seem to be getting narrower and narrower. And in fact, if you look down here at the summary statistics, the mean, so the average of samples of size 1 was just slightly different than 0. And if you're doing this on your computer, by the way, you'll come up with different numbers for all of these because these are randomly drawn numbers from these distributions. But I guarantee all of your distributions will have a mean of pretty close to 0 and a standard deviation pretty close to 1. When you get to samples of size 2, the mean is still pretty close to 0, but the standard deviation suddenly changed. Instead of 1, it's now down to around 0.71. And for 9, the mean is still pretty close to 0, but the standard deviation is close to 0.33. And for 25, again, the mean is close to 0, but the standard deviation continues to drop. It's down to around 0.2, and then 0.14, and finally, when we have samples of size 100, the standard deviation has dropped to about 0.1. Well, this is a demonstration of something called the central limit theorem. The central limit theorem, well, first of all, it's not surprising that we started with a normal distribution, the standard normal distribution, the one where we have sample size 1. And when we draw samples of size 2, 9, 25, 49, and 100, we end up looking at the mean of those samples. The mean is following normal distributions as well. Seems to make sense. We started with a normal distribution. The means of samples of different sizes follow normal distributions. So that doesn't seem surprising. What does seem maybe surprising is that we keep getting a narrower and narrower range in this distribution. It's still centered on 0 throughout, but the standard deviation, a measure of how, on average, how far away the mean is from that mean of 0, is getting smaller and smaller. And that is central limit theorem. It says as you take samples of larger and larger sizes from a distribution, the mean of the mean of the samples that you're taking will on average be equal to the mean of the distribution you started with. Those are the zeros for these means. And the standard deviation is given by the standard deviation of the original population divided by the square root of the sample size. When the sample size is 1, the square root of 1 is 1. You're getting back the original standard deviation 1. When the sample size is 2, the square root of 2 is about 1.41. 1 divided by 1.41 is about equal to 0.71. Standard deviation is about 0.71. The square root of 9 is 3. 1 divided by 3 is about 3.33. Standard, so 1 divided by 3 is about 0.333. Standard deviation, 0.334 here. 1 divided by the square root of 25 is 1 divided by 5. Standard deviation should be about 0.2 here. Look at 100. 1 divided by the square root of 100 is 1 divided by 10, 1/10. Standard deviation is about 0.1. So this seems to be reproducing what the central limit theorem says. What's even more amazing, though, is not that. It's let's change these distributions so that instead of a random normal distribution, we put in, let's say, a random uniform distribution. Immediately notice that the distribution changed. Let's see what it looks like. What is a random uniform distribution? Well, it ranges from 0 to 1. Everything is pretty much equally likely. The only reason why it's not completely flat here is I only am looking at a sample of 10,000. So with 10,000 points, it's a little jagged, but roughly the probability of being in any range from 0 to 0.1 or from 0.9 to 1, they're about equal. On average, what do we get? 0.5. So on average, you'll be right around the middle from 0 to 1, 0.5. The standard deviation is actually given by 0.288. Remember, I told you the standard deviation can be thought of as roughly the average distance from the mean. If everything between 0 and 1 is equally likely, and the mean is about 0.5, on average, we should be about 0.25 away from 0.5. This point will be a full half 0.5 away from the middle. This point out here at 1 is about 0.5 away. But then we have points closer and further away. On average, we should be about 0.25. The reason why the standard deviation is 0.288 instead of 0.25 is because, remember, it's calculated by looking at how far away points are from the mean, squaring the distance, summing those, and then taking the square root of that divided by the sample size. So we're looking at kind of the average distance, but it's not really the average distance because we squared those distances. So that's why the standard deviation comes out a little bit larger than 0.25, but you can intuitively think of it as sort of the average distance from the mean, roughly that. Let's see what happens when we change the formula for these other sample sizes. Instead of using the random normal distribution, we replace it with a random uniform distribution. And I'm going to do this pretty quickly for all of these. Gotta be careful when you use formulas to make sure that the blue box is around what you're about to change. So for instance, when I go into this formula, if I do something, it'll change the entire blue box. Once I focus on just that random normal distribution, I can change that. Okay, now let's see what we get if we analyze all of these distributions. Our uniform distribution, sample of size 1, looks like the original uniform distribution. As soon as you average two numbers, take a look at what happened. It's starting to become mound-shaped. It looks more like a triangle. Now, why is that? Think about it. You're taking two random numbers from this distribution on the left. The likelihood of getting two numbers that are both pretty much near equal to 1, that's much less likely than getting a number that's really high and then a number that's considerably lower than that. The odds of getting two numbers that both are around 0 starts becoming pretty small. It's much more likely if you get one number that's close to 0, you're going to get another number that's somewhat higher. So we have built up the probability of being sort of near the middle of this distribution. It isn't what I would call bell-shaped. It's more like a triangle shape. When you get to sample of size 9, this is distinctly starting to look like a bell-shaped curve. 25, even more so. 49 and 100 look pretty much like bell-shaped curves. And in fact, they are pretty close to normal distributions. Think about what the central limit theorem says. Take the sample size, the standard deviation of the original distribution, 0.288, divided by the square root of the sample size. Let's look at 100. It's an easy number to calculate. If you take 0.288 and divide it by the square root of 100, we should be looking at 1/10 of that. And look at the standard deviation out here, 0.0289, almost exactly 1/10 of what we started with. Or you look at 25, square root of 25 is 5, 1/5 of 0.288, 0.0578 is pretty close to that. So in fact, the central limit theorem seems to be work for a distribution that looks nothing like a normal distribution. So here's technically what the central limit theorem tells you. As you take larger and larger samples from any population, it could be normal, could be uniform, could be skewed, it could be any distribution. The mean of those random samples will approach a normal distribution with a mean equal to the mean of the population you're drawing it from, and a standard deviation given by the standard deviation of the population you're drawing it from divided by the square root of the sample size. A couple of key words in that. The central limit theorem says that it approaches a normal distribution. You can see it approaching a bell-shaped curve. How big does a sample have to be? The rule of thumb is that if the sample size is 30 or greater, you can pretty much be assured that the mean will follow a normal distribution. It looks like it's already following a normal distribution with a sample size of 9 here. But for very skewed distributions, this is still a symmetric distribution, a uniform distribution. For very skewed distribution, a sample size of 9 is generally not enough. Even 25 might not be enough. The rule of thumb is if you have a sample of size 30, you can pretty much be sure that the mean of that random sample will follow a normal distribution. It has to be a random sample, that's another key step. And the standard deviation is given by the standard deviation of the original population divided by the square root of the sample size. So I've demonstrated the central limit theorem. Let's see how that applies now to our data set. Go back to this time spent watching television and movies. Let's look at the distribution. Let me put it horizontal view. Clearly not a normal distribution. It's a very skewed distribution. The mean was 189 minutes. The standard deviation is 196 minutes. So even though the mean is about 3 hours, the standard deviation is a little more than 3 hours. That means on average, you can think of each person being about a little more than 3 hours away from the mean of 3 hours. So on average, people could range, the average person could be 0 minutes, not watch television at all, to watching 6 hours, twice as many hours. That's a very large standard deviation compared to the mean. It's even greater than the mean. But what do we know about the average? We know the average in this sample was 189 minutes. But if we're looking at a sample of size 9,435 randomly selected people, the standard deviation for the mean of that sample should be the standard deviation of the population, which is 196 approximately, divided by the square root of 9,435. And that's what this next number is, standard error of the mean, 2.01. So what that means is you can say that the mean for a random sample of 9,435 people will be approximately 2 minutes, on average 2 minutes away from the mean of 189 minutes. Each person varies tremendously, but the mean of a sample of this size is much more predictable. If we took a different 9,435 people and asked them how many minutes they spent watching television, the mean of that next sample is likely to not be very far away from 189. And in fact, that's what this confidence interval tells you. It's a 95% confidence interval. And it's constructed by saying, we know the central limit theorem says as long as the sample size is more than 30, which is well more than 30 here, the mean of any sample that we take of 9,435 people will follow a normal distribution with a mean equal to the population mean and a standard deviation given by that population standard deviation divided by the square root of the sample size. And that's telling us that we're 95% confident that the real mean number of minutes of television watched ranges from 185 to 193 minutes, which is approximately 1.96 of the standard errors around the mean. Essentially, the way that confidence interval is constructed is by saying we need to go approximately 2 standard deviations on each side of the mean that we found. And the standard deviations we use is not the 195 minutes, it's the standard error that's associated with a mean of sample size 9,435. This is what allows us to be pretty confident that that the true mean number of minutes watched ranges between 185 and 193 based on our sample that we have here. So you wouldn't want to say, we know from our study that people watch 3 hours of television per day. That happens to just be the mean from the sample that we took. What we can say from this, though, is that if we took different samples of 9,435 people, 95% of the time we're going to get within about 2 of these standard errors, within about 4 minutes of the 189. That's the 185 to 193. Is that 95% of the time will be within 4 minutes of the 189 that we got in this particular sample. So we can say that we're 95% confident that in the entire population of the United States, the average number of minutes watched is somewhere between 185 and 193 with 95% confidence. If you want to be more confident, you'd have to make a wider confidence interval. So for instance, you can go for a 99% confidence interval, and that would say you'd have to say a 95% confidence, it's between 183.8 or 183.8 and 194.2. It's a bit wider than 185 to 193 to be 99% sure. So the central limit theorem allows us to take a random sample with any distribution. This is a distribution that is far from a bell-shaped curve. And based on that sample, we can still make statements about the population we drew the sample from. And that's a very powerful result because there's no way we're going to know and be able to measure how much television all Americans, all 330 million of them, watch. But we can take a random sample of a fairly modest size here and be able to have a fairly narrow range in which we can say something about what the mean of the entire population is based on only the sample that we took. So that's the basic thing that underlies all statistical inference. We're not going to use this very much at all in this course. In future courses, you'd be more concerned about making inferences from the population. We're just going to be describing, for the most part, the populations or the data that we have, which is usually or often going to be a sample. Sometimes it's going to be population data, but most of the time we'll be looking at a sample drawn from some population and trying to use that to describe the population. In statistical terms, that would require some assessment of how certain we can be or the range in which the true population lies. Anytime you look at a political poll or any kind of social survey that's done, they'll often talk about the margin of error. And the margin of error is usually for a 95% confidence interval, how far away from what you got in your sample might the true population be. So if you're doing a political poll and you say candidate A has 35% of the population's support and the margin of error is 4%, that means that you're 95% confident that the true support is between plus or minus 4% from that 35%. 31 to 39% would be the 95% confidence interval. So usually for good surveys, they should tell you what the margin of error is, and that's what it means. It's for a 95% confidence interval, it ranges between these two numbers, just like a 95% confidence interval here tells you the true population mean minutes watched of television per day is between 185 and 193 minutes. It is kind of a miracle that this is possible to do based on a sample. You should bear in mind it does require it being a random sample, and random samples are hard to come by in real life. Most of the time we are using what's called convenience samples, which is just the data that happens to be available to us and is almost certainly not a random sample. And if it's not really a random sample, you can't really apply statistical theory, but we do it all the time because usually that's all we've got to work with is whatever sample we were able to get. We'll talk about that more in class. But if it is a random sample, then all of the statistical theory does allow you to quantify the range of uncertainty about the population data that you're interested in, what the mean is for the entire population based on just this small sample. And that covers basics of probability and statistical inference as quickly as I can do it.